Alright guys, so now that we've talked about the different layers of Earth and we've talked about how plate tectonics affect Earth, let's talk about what those cause, those moving plate tectonics, okay? So we are going to start talking about earthquakes and volcanoes. So, as we remember, the lithosphere is the crust and upper part of Earth's mantle, okay? And here we have the parts labeled. So number 1, which is the innermost area, is the inner core. 2 is the outer core. 3 is the mantle. 4 is the crust. So plates are large pieces of the lithosphere, if you guys remember. So, and if we recall the theory of plate tectonics, that was the idea that Earth's crust is made of moving plates. And there's plate boundaries, and this is where the plates meet together. And scientists think that as the magma in the Earth's mantle moves, it's like a slowly moving river, and it causes the plate boundaries to collide or separate or slide along each other, right? So that's how we get the convergent, divergent, and transverse plates. So scientists believe the Earth is made up of large plates that float on the partly melted rock of the Earth's mantle. Pangea is the idea that the large landmass that sometimes have been thought of by scientists as existing a long time ago, because Pangea is when all of those puzzle pieces, as they call the continents, were fit together. There are no recorded observations of Pangea. Obviously, there were no cameras back then or people to take pictures, so therefore we don't have any record of those, but it is a scientific theory. So when these plates are shifting and moving, it's going to cause some effects on Earth. Well, one of those is earthquakes. So earthquakes often occur when rocks along the plate boundaries shift suddenly and they release that stored energy, and that energy bounces off everything and it creates havoc. Construction of large buildings and the movement of molten rock under a volcano can cause an earthquake. You see here, we have train tracks on this this piece of plate here and this piece of plate here, and we see that they're moving like this, so it's creating this like cliff, right? So those are called faults, and faults are breaks in the Earth's surface where rocks can move. So there's 3 kinds of faults, and they're determined by how the rocks move against each other. So there's thrust or reverse fault, there's normal fault, and there's a strike-slip fault. So a reverse fault is where rocks push together until a section of a rock moves upward. A normal fault are rocks moving apart, and a strike-slip fault are rocks moving horizontally past each other. So, earthquakes obviously occur below the surface of the Earth, and the focus is the beginning point of the earthquake. So this is where the movement begins. And the movement creates vibrations that flow out from the beginning of a point to a certain area depending on how big those waves are, and they are called seismic waves. The epicenter is the point on the surface of the Earth directly above the focus. So the focus is the literal point underneath Earth that the earthquake begins. And the epicenter is the spot on the Earth's crust where we are that is being disrupted. Okay, so we talk about these seismic waves. Let's look at waves. We've got body waves. These are the waves that occur beneath the surface of the earth. And then we have P waves, or primary waves, and these are the fastest moving. They travel in a straight path by a push and pull motion. Okay? Then we have S waves, which are secondary waves. These move slower and they move in an up and down zigzag pattern. So land waves are surface waves. They're the slowest moving, but they are the most destructive. Love waves are also in a back and forth zigzag pattern, and they are the fastest moving land waves. Rayleigh waves move in a circular pattern and they roll. They have a rolling motion that they use along the ground. So how do we detect earthquakes? Well, if we know there's seismic waves, scientists have developed a seismograph, which is a machine that detects the time and the measurement of the movement of the earth. So seismograms, they record the movements of the earth. So you have the seismograph, which is the machine. The seismogram is the part of the machine that records the movements. And then seismologists are the scientists who study the movement of Earth and study earthquakes. So, how do we measure these, you ask? Well, we have their Mercalli scale, which is based on the amount of destruction caused to man-made structures. So we're talking buildings, cars, anything that is man-made. Okay, so this is measured by observable destruction. So you're going to know if a building is experiencing destruction because you're going to look at it and it's going to be crumbling or it's going to have cracks. It's going to be an observation-based measurement. Okay, then we have the Richter scale. Now the Richter scale measures the magnitude of an earthquake's seismic waves and it assigns it a number. Okay. So the magnitude is the strength of the seismic wave of an earthquake. Features that help structures withstand earthquakes are concrete that is reinforced with steel rods, a foundation that's laid in rock, steel framing. Okay, so earthquakes also cause other disasters. So they are a tsunami, which is a giant ocean wave triggered by an earthquake, a volcano, or a landslide. And there's some other catastrophic events associated with earthquakes, and they are volcanic eruptions, landslides, right? So then we have volcanoes. So earthquakes are from the plates shifting and interacting, right? And they create these earthquakes. Well, volcanoes are magma. They're molten rock that's under the earth. And a volcano occurs where a crack in the Earth's surface allows magma and gases to come to the surface. And a volcanologist is a scientist who studies volcanoes. Magma chambers are pockets of molten rock in the Earth's lithosphere. And lava is the hot, molten rock that breaks through the surface of the earth. So remember, the molten rock that is under the earth is magma, and the molten rock that breaks through the surface of the earth and goes out is lava. And then we have vent, which is the opening in the surface of the earth, which the lava flows. So the vent is like the top part of the volcano. So it looks like, you know, a soda bottle at the top there, that would be the vent. And then we have a crater, which is the bowl shape at the bottom of the main vent. That's what holds all that molten rock before it escapes. So if we look at the diagram here, we can see that we have volcanic ash, which are jagged bits of crushed rock that are thrown out of the volcano. We have a volcanic cone, which is the funnel-shaped mound. So let's look. Number 1 is the crater. So here's number 1. Number 2 is the side vent. So this is like a vented area where other lava escapes, caused usually by pressure. Then we have the main vent, which is this big area here, which is just pushing this magma out. Then it comes lava, right? And it's flowing down the side of this volcano here. And then this is that magma chamber that's just holding all that magma, getting ready to throw it out of that volcano when it erupts. So, locations of volcanoes. Volcanic activity may occur under the ocean, at hot spots, along plate boundaries, and along the Ring of Fire. The Ring of Fire are active volcanoes around the edges of the Pacific Ocean. Underwater eruptions, or as some people call them, submarine eruptions, are 20 times more frequent than eruptions on land. Hotspots are places where a pool of very hot magma rises toward the surface and forms new land, islands. Well, how often do they erupt? Well, volcanoes can have more than one kind of eruption because one eruption can take the conditions inside a volcano, causing it to erupt differently the next time. So an active volcano is one that has erupted at some point during a recorded time period and is expected to erupt again. A dormant volcano has erupted in the past, but is currently inactive and it's not really expected to erupt again. And then we have an extinct volcano. Those don't have a recorded eruption and they are not expected to erupt in the future. There is no guarantee, though, that it will remain extinct. So they're not like animals, okay? Extinct volcanoes can become active. So we can classify these volcanoes by the type of eruption, right? So we have a Hawaiian eruption, which is runny lava and little or no cinder, which is like the burnt pieces, right? Or ash or steam. It's usually quiet and it may continue for a long period of time. Then we have the Strombolian eruption, which is just a fountain of lava that runs down the sides. Then you have a Vulcanian eruption, which is violent and it causes a loud explosion and it sends lava and ash and cinders and gas into the air. And then we have a Pelian eruption. And this produces a pyroclastic flow, which is an avalanche of red hot dust and gases, and it's thrown out of the volcano. And then we have a Plinian eruption, which is the most powerful. It spews lava, it blows gases, ash, and debris into the atmosphere. It causes a lot of damage to the ozone layer. And then we have the pyroclastic flow, which is a high-speed flow of very hot gases and dust. And these volcanoes have lots of effects, okay? So we have VOG, which is kind of like fog, but it's volcanic fog. So it's volcanic gases that pollute the air and can cause acid rain, which is rain that has a very, very, very bad environmental toll that it takes, okay? So acid rain can kill plants and animals, and this can also cause respiratory problems in animals and humans. So the gases, ash, and dust of volcanoes can can cause cooling in the weather. There's some dangers of volcanoes, obviously. Don't play in them, please. So there's debris flow. So when part of the mountain collapses and mud and rock fragments, they surge down the mountain. So let's talk products of volcanoes. Their soil is actually really rich in nutrients, and a lot of times that's where you can find valuable gems. Igneous rock, which we all should know, is formed as magma and lava cool and harden. Okay? There can be other thermal eruptions, like hot springs, which is a heated pool of warmed groundwater. So I don't know if any of you have ever been to, there's a really cool town in Arkansas called Hot Springs, Arkansas, and there's all kinds of natural hot springs all over the town. It's beautiful, but you can't touch the water because it's really hot. Trust me, it's really hot. There's a sign that says, "Don't touch the water." And Mrs. Jacoby was like, that sign's not for me, and I touched the water, and it was definitely really hot. So I don't suggest it. Please listen to signs. Don't be like me. We have geysers, which is a hot spring that blows steam and water into the air. I don't know if any of you have seen Old Faithful. If not, you should look it up online. It's really cool to see. That is a geyser, hot spring. Mud pots are pretty cool. Those are a hot spring, but they contain mud. So the mud bubbles. It's pretty neat. All right, guys. So that's it for volcanoes and earthquakes. So these are all effects of tectonic plates moving underneath of us while we are feeling earthquakes move and rumble. We can't really feel the volcano because usually you're pretty far away from it, but you can see it and smell it. When volcanoes erupt, if it's a really large eruption, you'll see, smoke and dust and lava shooting off into the sky, but sometimes a volcano can erupt and it be very small and, quite frankly, just not really that exciting. So I'm going to play a little video for you, and I want you to watch it. And then afterward, if you guys complete your assignment, I would appreciate that. And that will be it for volcanoes and earthquakes for today.
Hello. Today on Consider the Following, I'd like you to, consider the following. You and I are sitting on the Earth's crust, and it seems pretty solid, doesn't it? But now scientists believe that the Earth's crust is actually made of plates. Not cheap plastic picnic plates like this, but tectonic plates. And tectonic is from the Latin word for build. So the Earth's crust is built of plates. Plate tectonics. And the plates are floating on the Earth's mantle, which is molten metal. And it's kind of like corn syrup. In fact, scientists actually use corn syrup like this to do studies of what's underneath the Earth's crust. Scientists first caught on to the idea of tectonic plates when they realized how well South America seems to fit in next to Africa. Not that bad. So take a look here. Here we have the camp stove of science. And in it we have models of tectonic plates. See, right now they're all together. And scientists believe that at one time, all the plates of the Earth's crust were one piece called Pangea. And Pangea, well, that means whole Earth, see? Not that bad. Let's say this is the Earth's crust. See, where the plates, the tectonic plates, are spreading apart, that's where we get volcanoes. And where the plates are coming together, that's where we get mountains. Now, the plates are still moving even today. In fact, North America is moving away from Europe about this much every year, about 2 centimeters, about an inch every year. Well, thanks for joining us on Consider the Following.
Okay, it's real important to have shades on in here, glasses, because sometimes things will pop in here. This is molten glass. Watch what happens.
Take a look at this. It's a mountain. Well, actually, it's a volcano. Volcanoes are formed when hot, molten rock from deep inside the Earth finds its way to the surface. Now, this isn't hot, molten rock. It's a mild acid. To help it find its way to the surface, we'll add some sodium bicarbonate. This will be like a hard rock right above the molten rock from deep inside the Earth. See, the pressure builds up and it builds up. And eventually a volcano will erupt. It'll blow its top. It'll explode. explode.
When?
Anytime now. There it goes. You're saying, Bill, you know, I've made volcanoes like that in my kitchen. Maybe better. I mean, that's it? That's it? I mean, what's the big deal? What's the big deal? Take a look. Volcanoes can blow down entire forests in just a few seconds. They can reroute rivers and form new lakes, carve new valleys, transform entire landscapes in a matter of hours. And that's what happened around here when that mountain right there blew its top. It's Mount St. Helens, and it erupted in 1980. It's in the Pacific Northwest of North America. Now, there are different types of volcanoes. They don't always explode when they erupt. Some volcanoes ooze. Now, when I say ooze, I'm talking about hundreds of thousands of tons of rock. At well over 1,000 degrees Celsius, they come out of the earth and they cool off to make new land. Land that you and I live on. See, there are different types of volcanoes, but they all do the same thing. They all build up the Earth's surface.
Since the Earth was young, volcanoes have hurled fiery rock from the planet's interior to its surface.
The Richter scale is a way to compare the size of one earthquake to the size of another. Now, the ground can move in all different directions, but to start out with, let's say it's moving up and down, like this. See how we have a nice smooth curve? That's from the ground moving this way. Now let's say we have a bigger earthquake with a bigger ground motion. Let's say we have one 10 times as high. Like this. See how this one is 10 times higher than this one over here? So then the ground would take on a shape something like this. Same nice curved shape, but this stack of chips is 10 times as high as the one over there. But look how many more chips there are. You see, it takes a lot more chips to keep the curve in the same shape. The chips are like the energy in an earthquake. So when the ground moves 10 times as much, it has a lot more energy, about 32 times as much energy. And we have 32 times as many chips. Now, because the numbers can be very small or very large, Richter came up with the idea of using tens. See, let's say we have an earthquake of magnitude 1. Well, it's going to have some ground motion. We'll call it 1. Now let's say we have another earthquake of magnitude 2. Well, its ground motion is going to be 10 times as much. We just add a 0. Then for an earthquake of magnitude 3, we add another 0. So look, an earthquake of magnitude 3 has 100 times the ground motion of an earthquake of magnitude 1. And it has a lot more energy. Now, since Richter came up with this, a lot of other scales have come along. But they all work in about the same way. The bigger the magnitude, the bigger the earthquake. And the bigger the energy there is to knock stuff over. You weren't supposed to see that.
Oh, sorry.